Well, good morning, and this is what we learned, the Ohm's law, which relates the resistance of a resistor, any passive device in a circuit, potential difference between the ends of that device and electric current traveling through, and for some situations we know additional relationships, the junction rule, basically a law of conservation of charge, and the rules for equivalent resistance, which basically a manifestation of the Ohm's law for specific situations. And we have several simple cases to keep in mind. First of all, the battery. No matter what we have connected to the battery, a simple circuit, a very complicated circuit, that doesn't matter. The battery is just a source of a fixed voltage, and it doesn't affect the circuit any other way. It has no resistance. Now, a wire, any ideal wire, has no resistance, and if we apply a law, Ohm's law, to two ends or 2 points in a wire, because R equals 0, hence delta V equals 0, which means a wire does not change electric potential. In a wire, electric potential remains constant, the same. It only changes where? Well, it only changes here when a resistance is encountered, and well, potential number 1, potential number 2. That's what the Ohm's law says. But also, there might be a situation when a circuit has, well, some complicated part, wherever it is, doesn't matter. But also we have a single resistor similarly connected. But is it? No. A connection means that both ends of a device should go to some part of a circuit. And here, only one end is connected, second is not, which means electric current has to be equal to 0, because the electrons cannot travel through, they cannot leave that end, it has to be connected. And because electric current now is 0 for this particular device, well, first of all, it doesn't affect the rest of the circuit. We can just remove it. Doesn't make any difference. But also, it means there's no potential difference between the ends. So potential here and there also are same. Well, those are handy just points. We're going to use them once in a while. And let's do one example related to calculating a resistance. In this case, a resistance of a wire made of copper. And all we have to do is just practice in using scientific notation numbers here to calculate the resistance. Copper, what does it mean? It means we go online and we search for the resistivity of this material. And the only tricky part might be is a unit. This is ohms times the meter, a standard unit which belongs to international system of units, but very often it would have been millimeters and micro ohms or something. But here we just have to use this number, 1.678 times 10 to the negative 8. This is the first number, the resistivity. Now, the length, 10 meters. And the second relatively tricky part is calculating the area. But in this situation, for the sake of clarity, the wire is not round. For a circular wire, area equals pi r squared. But this is a square wire, so area equals length times width, and all we have to do is just convert millimeters into a meter. That's it. So now we just have to collect all the zeros. So 10 to the negative 8 plus 1 plus 6 0.1678 ohms. So 10-meter long wire usually used to actually make a coil. And we can see that because copper is a very conductive material, the resistance is very low. That's why people use copper. Plus it's cheap to manufacture. Now, this is a visual representation of what is happening inside a simple circuit. So we have a battery, which is acting like a pump. We have a passive device, and every battery has two electrodes, positive and negative. And first I want to ask you, why is negative equal to 0? What do you think? The potential, the electric potential, yes? Yes, because we always can set, to 0 any potential anywhere and measure all electric potentials around relative to this. And like we did with potential energy, we choose the 0 where we know it will be the lowest potential, so all other will be positive automatically. Now, relative to this value, the positive electrode of the battery has a number we call EMF, that fixed voltage provided by the battery. And if we look at fictional positive charge positron, it will be repelled. Plus and plus, they repel each other. So it will be pushed away, but because a wire has no resistance, it will be sliding down this wire with constant velocity, like a box sliding on the frictionless surface. So we don't have to keep pushing it. Only when it encounters the resistance, it's like a rough patch with the friction. It has to, well, because of the resistance, it slows down, but now electric field picks it up. Where do we get electric field from? From potential difference, higher potential, lower potential. And we know delta V over G is electric field. That electric field propels the electrons. But again, net force will be 0. There's force due to resistance, force due to electric field. So electrons or positrons still travel with constant velocity. And then they encounter another ideal wire, so they again slide down with constant velocity without resistance. They reach this end. What's happening? Because they're positive on their own, they cannot cross the wire. So what's happening? Little demons, take them and bring them over there. We call them chemistry, those demons. That's it. Diffusion. And they repeat the circle again and again and again. That's it. And of course, electric current does work. We use it every day. We use it at home, at work, everywhere. And first of all, the source of that energy comes from the battery. It's the only energy source in any circuit. EMF, those little demons, chemical reactions, represent the source of the energy. And because of that, electric field does work on electrons, yeah? Make them move. But electrons collide with atoms, and after every collision, every atom starts moving a little bit faster. If kinetic energy increases, that means temperature increases. So, and if it's high enough, we can use it for different purposes. So, question. I'm going to check your answers in a half of a minute. My expectation is everybody will choose exactly the same answer, which is what? What do you think? Different? Same letter, why is it different? So again, it's a matter of the limitness of alphabet. We have much more physical quantities than letters. And we have to remember the exact meaning of each letter in every equation. And if we don't, we can make a mistake. And see, some people think it's the same. Wrong. The first equation tells us the amount of heat related to temperature change. Second equation is a definition of electric current. So do not confuse and do not use different values, different quantities are the same, even if the letter looks the same. Well, of course, actually, we can calculate the amount of heat a bulb, for example, emits. But for that, we need to know how to calculate the amount of work electric current does. And, well, first we have to start from a very simple situation. One charge travels a certain potential difference from potential 1 to potential 2. How much work does the electric field do on it? Well, lecture 3, the work done by electric field on a charge is equal to this. Nothing new. In our situation, that single charge, of course, is an electron. Yeah, an actual particle traveling through wires is an electron. So, if we wait a certain amount of time, many electrons travel, right? So, for each electron, this amount of work is done. But for n electrons, we just have to multiply this amount by n. But this actually represents what? Just the total charge traveling through the wire. So this is how we can calculate the work done by electric field on electrons. But those electrons being resisted by collisions, but those collisions exert on average force which opposes the electric field, and the work done by that force should have the same magnitude but opposite value. Now, if the work done on electrons from atoms is not zero, that means the work done on atoms from electrons also is not zero, same magnitude, opposite value. So this basically tells us, again, if we want to calculate the work done by electric current, we just have to do this. It's the same amount of work. Of course, we neglect any possible energy loss. So now, what can we do? Well, according to a definition of electric current, that thing we can measure charge and time related, so we can replace charge with current times time. But this is the work done over a certain period of time. In practice, we don't usually use work, we use power. Power is the work done by, well, a force or a system per second. This is the official definition of power, well, average power, but if electric current is constant. So what we have is a very simple expression. Electric power, that's what you read on a label on any device. If you buy a bulb, it says 100 watts. Watt is a unit of power. And the symbol for the unit of power, a unit of power, is a capital W, which is same as work. So again, do not be confused. This is the unit of power in international system of units, joule per second watt. And so 100 watts, that means that bulb dissipates 100 joules every second. That's it. If you buy a TV, it tells you how much energy it uses every second. And of course, if you use it over a period of time, you can calculate how much work is done. Now, there's another law we can use, the Ohm's law. And the Ohm's law relates electric current, voltage, and resistance. So from original expression for the electric power using Ohm's law, we can write two more expressions. We had a similar situation when we were calculating the energy of a capacitor. There's an original expression and two more which have been derived mathematically, algebraically. So here what did we do? We just replaced voltage with current times resistance, current times current, current squared resistance. And here we replaced electric current with voltage over resistance. Which do we want to use? Doesn't matter. It's a matter of convenience. Again, sometimes we already know voltage and resistance. In that case, we would be using the last expression. And we will talk later about the power transmission. Of course, to generate electric power, we have a plant which does that, power plant. And well, this is a picture of atomic power plant. Now, next step, how do we measure all of those things? Well, we have devices which do that. In this situation, we see how would we measure the voltage across a device. Well, first we have to make a circuit. And when we make a circuit, we should imagine ourselves that we are a tiny positron which travels So we have to complete the circuit, the battery, the bulb. Don't fall. The battery. Of course, I could place a switch in it, but this is also my switch. That's it. And now I need the device. I have to plug it in. I have to turn it on. And now this device measures voltage. It is set to measure voltage. Yeah, I could use different settings, but right now, voltage. And a voltage is a difference between two potentials. So I have to connect one wire to one point in the circuit, second to another point in the circuit, and read the number. Bless you. 5.5 volts, that's it. But if I want to measure electric current, I need to count the number of electrons traveling through. It's like a water meter. So charges must travel through this device. And again, there are tiny demons, they count. First electron, second, third, fourth, then multiply by the charge, 1.6 times 10 to the negative 19th, then divide by time, and give the electric current. So in order to make charges travel through the ammeter, I have to break the circuit first, and I have to deflect the electrons so they would travel through. This is actually set to measure the resistance here. It's voltage, and actually all devices, including those which you will be using, similar, they can measure different type of electric current and different type of voltage. We call them DC and AC, and DC means direct current. Direct current means it's constant in time, and that is happening when we use the battery. AC means alternating current. Alternating voltage is what we use in power outlet. It changes in time. So we have to use settings accordingly. If we use a battery, we have to use a DC setting, direct current. So now I have to break the circuit, to break it for you. Okay. Everything is dead now. But what do I do? Well, so those positrons should travel into and then out. So far, the circuit is still broken. Still broken. What's wrong? Oh, also I have to measure current. So 268 milliamps. And if we know the voltage, 5, and if we know the current, well, let's say 0.3, we can calculate the resistance of this bulb, more or less, because the resistance, actually, no, it's not written here. The resistance will be equal to voltage over current. That's it, in ohms. Well, this is how we do it with a simple circuit. Question. So I have to break the circuit again. I don't need to measure electric current anymore. Turn it off, move it away. You are measuring voltage using your multimeter, and the number you read is negative. Does it make any sense? Or if it does make a sense, what does it mean? That's the question. You know what? I don't like orange anymore. I prefer red. Put it back. What happened? This question is about what? It's not about physics. It's about engineering. It's about how that device works. And the device measures potential relative to another potential. What relative to what? Well, every device like this, see, has the red terminal electrode, the black, and the black always represents the lowest potential, lowest. I cannot hear myself. Can you hear me? Okay, thanks. So this is supposed to be the lowest one. What does it mean? It means that in reality, this end of this device has a higher potential. And we always can fix it by just switching the electrodes. High to high, low to low, positive. If it's negative, that means we switched by any reason the electrodes. The one which has to measure lower potential actually measures higher potential. That's it. And in this situation, if we finish the circuit like it was on the previous slide, there is a battery right here. And so I want to, and now which is which? Well, in this situation, this is plus, this is high, so this electrode represents the red, and this the black. So the black, the one which is supposed to measure lower potential, is connected to a place with a higher potential. Well, we have solved this problem. Now, how much energy does it dissipate in 10 seconds? Well, energy dissipates in 10 seconds. Means how much work electric current does in 10 seconds. So work equals power times time. Time is 10 seconds. How do we get power? We have three equations, and what do we know here? Everything. We know voltage, we know current, we know resistance, so we can pick up any equation. For example, just current, voltage, time. Current is 0.4, the voltage is 3, the time is 10 seconds, 12 joules. That's it. So this is the same slide with one additional line about the power. Question. So we have a battery connected to a resistor. In this situation, only one source of EMF and one device which draws electric current. This very circuit. The battery, the bulb, and the EMF of this battery is given 6 volts. So the question is, what is the value of electric potential right here where the bulb begins? So you have to pick your answer and enter it. And that's the question number 4. Close. Now, okay, still collecting data. If you think, let's just vote for now. If you think the electric potential there equals 1 volt, please raise your hand. 2 volts. 3. What does it mean? More or less? 4. 5. 6. Everybody has to raise a hand. It's 6. It's 6 because, as we just said a couple of slides or so before, a wire doesn't change electric potential. So electric potential at the negative electrode is set to 0. How do we know? We can read. So this potential will be higher than 0 by EMF. 6 higher than 0 means this potential is 6, and a wire does not change electric potential. Remember that. Forever. All right. So, next question. Now I'm going to place a switch in the circuit. This one, this thing. And this switch will be opened. So I have to reconnect the bulb to the switch. And I need another wire now to connect the switch to the battery. Like this. You know what? The battery, the switch, the bulb, and now of course we need that device which measures voltage. Does it measure electric potential? What do you think? Does it measure electric potential? That's a yes or no question. No, it measures potential difference. So that's why we use 2 wires. We cannot use just 1 wire. It won't work. So last chance to look at the possible answers and choose yours. Now, to reason through, you have to use the knowledge that a wire does not change potential. So, electric potential here, we always set it to 0. Don't have to. It's just easier. So, electric potential here will be equal to 12 volts. This resistor R has the resistance of 6 ohms. So the Ohm's law, which relates the voltage, current, and resistance, tells us that electric current through the resistor should be equal to 12 over 6, 2 amps. There are 2 regimes. First, when I drink coffee over there. Second, when I drink coffee while walking. What do they mean? So you have to start screaming. It's wrong. What is wrong? What is wrong? Anybody? Yes?
It's not closed, so there's no current.
The switch is open. Electrons cannot jump across an open switch. There is no electric current. It cannot be two. If it... wrong. It's not mathematically wrong. It's physically wrong. Electric current must be equal to 0 in this situation. How do we use it? Well, we know that a wire does not change electric potential. So electric potential here, 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 all the way up to here will be equal to 0. 0 volts. Now, electric potential here equals what number? Here. 12. And a wire does not change potential, so up to here, it's still 12. Now, what is happening inside this resistor? Does it change potential or not? That's the most important question. If there is no electric current, there is no potential change. Potential change through the resistor equals current times resistance. And because there is no electric current, there is no potential change. That was one of the rules. So electric potential does not change through this resistor. And then another ideal wire, yeah, so electric potential remains 12 all the way up to the second end of an opened switch. In that case, if we measure now potential difference, what number should we read? Well, but my battery is not 12-volt battery. This is a 6-volt battery. So what should I read? 6. And this type of reasoning is important. Actually, it has a name, tracing potential. We trace electric potential. We trace it. And what's going to happen if we close the switch? Well, now, if the switch is closed, it becomes an ideal wire, has no resistance at all. And if it has no resistance, even if electric current now is 2, or whatever for this battery is, there is no potential difference here because a wire does not change potential. Let be the light. So, next situation and the question. We have two different resistors connected. How do we call it? What type of a connection? Series? Yes. So I need a second bulb and an extra wire. Oh no, I don't need actually because I removed the switch. So maybe a different bulb. These are identical. Clipping an alligator clip to the banana plug. That's what you get PhD for. Bulb number 1, bulb number 2. slightly different brightness, different resistance. The question is about what? Electric current. So we don't need this anymore. But we need this guy, which measures electric current. How do we do that? Well, we have to break a circuit and insert this device inside the circuit. For example, first time we can insert it here. Come on. Oops, something happened. Okay. The most common problem with any circuits is bad junction, bad connection. Okay. 210. Put it back. Now we want to measure this current here. $210. Now we want to measure this current here. So we break it and insert. $210. And of course, it has to be the same because they connected in series. So it doesn't really matter how many elements and what elements do we have connected in series. Electric current has to be the same. And again, electric current is basically the charge flow rate. If we have a device with a higher resistance, it might slow down electrons inside, but it means more electrons will be accumulated inside. If we have a device with a lower resistance, so they will travel through faster, but less electrons, the density will be different. So they always balance out in such a way, so charge traveling every second will be exactly the same. Now, let's solve this problem as, again, an example of using this method, tracing electric potential. We have a circuit here with with one battery and two resistors. One battery and two resistors. That's it. That's all we need to know. The rest is just an illustration of what is happening to potential. Yeah? Electric potential. Well, this symbol represents grounding. Every plug has a ground electrode. If you plug it in, you connect it to the earth. And that makes that electrode to have zero potential, zero electric potential. Only physical object may have zero potential. Humans never have zero potential. So the battery rises potential from zero to the EMF of the battery, and then through the circuit potential drops. How? Well, that's our goal. So first we have to just draw the circuit. Yeah, start from the battery. Then we have first resistor. Then we have a second resistor. And go back to the battery. So this potential is set to zero. So this potential is equal to unknown. That's what actually we are looking for. Find the EMF of the battery. All right. What we know is the resistances in electric current. This is liter R, 10, ohms. This is a big R, 20 ohms. In electric current, I equals 0.1 amp. Okay. If we know electric current and resistance, we can calculate voltage. So delta V1 will be equal to little r times I, 10 times 0.1, 1 volt. Now, this is the voltage across this resistor. This is the voltage between these 2 points. We'll call it A and B. And there is a point C. The voltage across the second resistor, delta V2, will be equal to what? It will be equal to R times I, which is 20 times 0.1, 2 volts. But each voltage, according to its definition, is just difference. For example, delta V1 equals potential at point A minus potential at point B, or potential at point B minus potential at point A. But of course, out of 2 choices, only one is correct. So please make your mind. Is it this difference or this difference? All right, now it's time to vote. If you think it's this difference, please raise your hand. Why? Can you offer the reasoning? There's no such a rule. There is a rule which tells us how to figure it out. The rule says electric current travels through the passive element from a higher potential to a lower potential. How does electric current point? Through this resistor, electric current points from A to B. That makes potential A higher, and the difference has to be positive. So we have to remember the rule first, and then we have to apply that rule. And about 2 volts, which is delta V2, should be equal to, according to the same reasoning, electric current through the second resistor travels like this. And that should be, that tells us that potential B should be higher than potential C. Now, we have special words which we use to describe a direction. For example, this arrow, describes a specific direction. How does it point? How do we call this direction? Up. Of course, that arrow points how? To the right. So when we say electric current through the first resistor travels, we have to finish up. Electric current through the second resistor travels, we have to say to the right. However, we also have a name for this direction. How do we call it? Clockwise. And this direction describes electric current in this circuit as the whole thing. So if we are asked, what is the direction of electric current in this circuit, we should say clockwise. The clockwise direction of electric current in the circuit makes it up through the first resistor, makes it to the right, through the second resistor, makes it to the left, through the battery, And the thing is, at this point, I have no idea how to say the same in Russian. So, what are we looking for? We are looking for the EMF of the battery. And EMF of the battery is equal to that fixed voltage it supplies to the whole circuit. And that should be equal to the difference between potential A and potential C. That's what it is. Because wires don't change potential. So from here to here, it should be same potential A. From here to here, it should be same potential C. And well, that will be equal to VA minus VB plus VB minus VC. And of course, as we knew it before, we have it proved again. It just equals to potential difference for the first element and for the second together, 1 plus 2, 3 volts. This is again a proof of the rule we've used before for resistors connected in series, and then before that for capacitors connected in series. The total voltage is equal to the sum of individual voltages for all elements connected in series. We just have it proved and used. Any questions? It's more about language than mathematics. Mathematics is really simple. All right, let's do another example very briefly. So what we know here, this potential we can set to 0 volts, 0, 0, 0, 0, 0, 0, 0, 0, and this is the voltage across the resistor. Now, electric current through this resistor travels up because electric current in the circuit is clockwise, which means from here to here, potential should increase. Now, that brings to two new different words: potential rise and potential drop. Those two words represent voltage. We just use it differently. We say the voltage across this resistor is equal to 2 volts. But from point 1 to point 2, potential rises. So we say there is potential rise from 1 to 2. However, from point 2 to point 1, potential decreases. So we say potential drops. This is just a slang electricians use, but sometimes it's also used in a textbook or in a problem. This is just a voltage with the indication of direction of basically electric current. Yeah. Because again, we know electric current always points from a higher potential to a lower potential, which means if we know direction of electric current, we can use it backwards. We can figure out which point has a higher potential, which point has a lower potential. So, 0 volts, 0 plus 2, 2 volts. That's a potential. And this potential does not change up to here. And now electric current through the second resistor points to the left. And against electric current, potential rises from 2 by 8. So what does it mean? It should be equal to 2 plus 8, 10 volts. And this potential does not change up to here. So this electric potential equals 10 volts, and this electric potential equals 12 volts. And this potential difference will be equal to 2 volts as well. This is just an exercise in using language. Potential, potential difference, voltage, potential rise, potential drop. And that makes it a resistor. How do I know? Through this element, electric current travels from a higher potential to a lower. This is an indication of a passive element. In an active element, like a battery, electric current goes from a lower potential to a higher potential because demons do that. Remember that. Well, and very quickly, exactly the same reasoning tells us, so 0, 0 plus 6, 6, 6 plus 8, 14. This electric potential equals 14 volts, but that 12, how can it happen? That's not a passive element anymore. That's supposed to be a second battery. That's it. Now, what do we do if we have several devices connected together? We know what to do. Bless you. First, we know that we can replace two resistors connected in series with only one resistor. What should be the equivalent resistance of this one? According to the rule, 6 plus 3, it should be 9 ohms. Connected to the same battery. This is the equivalent circuit, 12 volts. Now we can calculate electric current in this circuit. Electric current I should be equal to 12 over 9. 4/3 amps. But according to a definition of the equivalent resistance and equivalent circuit, the same electric current should travel here. So we just use this number back in the original circuit. What can we do now? Now we can calculate individual voltage. The voltage number 1 should be equal to same current times R number 1, 4/3 times 6, 8 volts. I could apply the Ohm's law again to calculate the second voltage, but I also know that for devices connected in series, if we add individual voltages, we should get the total voltage provided by the battery. So 12 should be equal to 8 plus whatever. That makes whatever to be equal to 4. Yeah. Delta V2 should be equal to 12 minus 8, 4 volts. Power. Okay. We can calculate actually 3 different powers. Power number 1, the work electric current does every second in the first resistor. It should be equal to current times delta V1. Current 4/3 times 8. V2, same calculation. But we also can calculate the total amount of work done every second on both resistors. That will be equal to P1 plus P2. However, the law of conservation of energy tells us that's supposed to be the amount of work the battery does on the whole circuit. And how do we calculate that? It should be equal to current times EMF of the battery, or current times the voltage of the battery. That will be the total current 4/3. The voltage is 12. And this is easy. 12 over 3 is 4. 4 times 4, 16 watts, joules per second. So most of the problems like that are very simple. Now, of course, an example for two resistors connected in parallel, but the first thing to do is to redraw the circuit. Now, actually, no. The first thing to do is to provide a new definition. So this is the equivalent circuit. But what does this mean? This is a shortcut for root mean square, which means that this voltage actually alternating AC, but it means we can replace it with a battery which has this particular value. That's it. That's what it means. If we have an AC source with a known RMS, root mean square value, it means we just replace it with a battery with a fixed value of the same number. That's it. So first we do that, a battery, a resistor number 1, a resistor number 2, and we set the EMF of that battery to 6, and this is R1, 8 ohms, R2, 4 ohms. So the hardest part when we have to solve this problem is drawing this symbol. And the advice is you start from legs, and then you add the body. Ohms. So of course we just have to apply the equation for the equivalent resistance of the resistors connected in parallel, and what does it give us? 3/8. But that's not the end of the calculation. Don't forget that we are looking for the resistance, so we have to flip the whole thing over. That will be ohms. Now we can replace this circuit with an equivalent one, R equivalent, and now of course we can calculate electric current. It has to be equal to voltage over resistance, which is 6/8/3. Right? And what can we cancel? 2, 9/4 amps. But now we can go back to the original circuit. We know that this electric current through the battery is the same for both, and here it splits. It has to split. A portion of it should go here, we call it I2, and a portion of it should go here, we call it I1. And we know that according to the junction rule, which is the law of conservation of charge, I1 plus I2 should be equal to I. How do we calculate I1? Well, we know the resistance, we know the voltage, so it just has to be equal to voltage over R1, 6 over, what is R1? 8. 3/4. And that's it. You can calculate I2 differently. That will give you the results. And of course, if you want, you can calculate the power. Just one more equation to use. Question. When you are using all your electronic devices, TV, the table lamp, wherever it is, a stand lamp, what kind of a connection, if any, do you use? And of course, the answer is in the schematic, in the picture, in the drawing. Oops. I should have okay. A missing slide. So you have a power outlet, and you have a bulb connected to it. You have another power outlet, and you have a TV set connected to it, etc., etc. But they're not independent. Yeah, you have a switchboard, and all wires go there to same incoming wires, and that makes them connected in parallel. And if you want to know how much do you have to pay, you can calculate your payment. You know your rate, well, hopefully. So all you have to do is just calculate how much work does every single device do. And you can read the power on the back of your device. And if you know how much time you use it, power times time gives you amount of work done by first device. Power times time gives you amount of work done by second device. And they do it independently. And then you just multiply total amount of work by the rate. That gives you how much you pay. Hopefully, the number you get and the number you get in the bill the same. You should check, just in case. Well, so that's basically why everything is important for us. Yeah? This material is being used every day and night. Question. Here I have two bulbs connected in series, connected in parallel. This question about two bulbs connected in parallel. And I'm going to switch for a moment. Oops, wrong switch. So how do I know which bulbs are connected in series and in parallel? I can read. But also I can see wires. Yeah. So there's a wire, then a second wire from the first bulb to the second, and go back in series. And here I have wire and wire, positive to positive, well, actually negative to negative, and here positive to positive in parallel. So these two bulbs have different nominal. This is a 40-watt bulb, this is a 100-watt bulb. You actually can see they have slightly different filament. This is a straight one, and this is like a semicircle. And if I plug it in, okay, and if I press the button, we can see the brightness of each bulb. And, well, you don't have to watch. Actually, let's do it with the camera for the record. They're bright, so you should kind of close your eyes a little. Which is harder to look at? This one? Of course, if it says 100 watts, it has to be brighter. That's what we use it for. So the real question is, what do you think is going to happen if I use the same two bulbs, but I will plug it in, connect it in series with each other? So here, I'm going to switch back here. The answer is, whichever has higher wattage will be brighter. That's it. And actually, what does brightness mean it means it emits more energy per second. It has a higher wattage. So if we calculate the power for the bulb number 1, and if we and if we calculate the power for the bulb number 2, 40 watt. First of all, they share something. When these two bulbs connected in parallel, which means to the same or different power outlets, what do they share? What do they have the same? Voltage. Yeah, parallel, bulb number 1, bulb number 2. Parallel means same voltage. So they draw different current because of that. And actually, we know that the root mean square voltage they have across is 120 volts. It's not the maximum. Yeah. The actual voltage alternates between 0 and maximum, but we can replace, if we could, the power outlet with a battery with this nominal 120 volts. That wouldn't affect anything. All right, so that's not a question to answer, but the result I'm going to show you. No, wrong. Right. The result you should expect should be completely opposite. Now the 40 watt bulb is actually much brighter, and this is barely dim, just a little bit of light. Same bulbs, but completely different behavior. Why? Well, it's all related to how much power it draws. And now, if we compare the power, okay. So now the situation is different. That's the same voltage. Now, let's call it R1. Actually, we don't know the resistance, but we will find it. And this will be a P1 40 watt bulb, R2 P2 100 watt bulb. What do they share now? Electric current. So higher power means higher brightness. That's what it means. More power, brighter bulb. Less power, dimmer bulb. But if I try to calculate power, well, number 1, I1 times delta V1, or power number 2, I2 times delta V2, this is what I have to do, right? P1 equals I1 times 120, and P1 equals 40 watt. So that gives me electric current 40 over 120, 4/12, 1/3 amp. I have no coffee left, but I have to fake it. And you know why? Because I made a mistake. Rules are rules. We can't break rules. Everything will be chaotic. So, what did I do wrong? Something Very, very wrong, yes. Exactly. Thank you. So, wrong. That's the only way we humans learn. We make a mistake, we find how to fix it, and we remember it for the rest of the life. Hopefully. So this is not 120. This is, we don't know actually what it is. We don't know what that is. So the equations are correct, but the number is wrong. Well, and we don't know the current. What does it mean? Well, it means we have to try a different equation. For example, since they have the same current, probably it's easier to have an equation with the current. So let's make a transition. P1 equals I1 squared times R1. P2 equals I2 squared times R2. And actually, hence, the current is the same. We don't even have to keep that symbol, subscript. Current is the same. Now we can see that in this situation, for the connection in series, the power is based on the internal resistance of the bulb, which means the brightness. And, well, this is what we need, the resistance. And this is what we don't know. This is a very common situation. We need it. We don't know it. So what do? Find it. That's the only way. We need it, but we don't have it. So we have to find it. How do we find it? This is how we find it. We go back to slide for connection in parallel. The number on the bulb assumes that the bulb is plugged in directly into power outlet, like in this picture. Hence, this power, P100, which is 100 watt, should be equal to voltage squared divided by resistance. Which voltage? The voltage of a power outlet, which is 120. So R will be equal to voltage over power, 120 squared over 100. But R40 will be equal to 120 squared over 40. So which of these two bulbs should have a higher resistance? 40. Denominator is less than in this fraction. Smaller denominator, larger result. You can just calculate the numbers. And I have a slide later. Yeah. 12 squared is 144. So 2 zeros, 144 ohms. And this will be, I think, 360. So now we can go back to the slide with the same bulbs connected in series. And now we know R1 is greater than R2, which means P1 is greater than P2. That's why when we have the same elements connected differently, it matters. Connection matters. Not just the element itself, also how those elements are wired up together. Well, we saw it because the resistance, and we just answered this question, so don't do that. which one has a higher resistance. This one, we have it found, we have it calculated. These are the numbers. This is for 100 watt bulb. This is for 40 watt bulb, 360. And I want to ask this question, but now this is a question number 8 because I skipped it. All right, choose one, whatever. If you 8 or 9 doesn't matter. 8 or 9. I have a power to figure out. So, what will happen to this electric current after we close the switch? First, we can do it mathematically. Second, we can do it physically, actually. And I'll prefer physically. But to do that, I have to build the circuit first. So I've got a battery, and I have a bulb connected to this battery, right, like this. And I have this device we call ammeter. It's supposed to be plugged in, and it isn't. And now it is. So red, black-ish. And so I'm measuring. Actually, I don't need this wire. I'm measuring electric current. Now I have a second bulb and a switch. How do I have to connect it? When the switch will be closed, this bulb should be in parallel to the first one. All right. This should go to the switch, and from the switch back to this bulb. Oops, I have to open it. When I close the switch, something should happen. So, anybody, please tell me, what do you think will happen with this number? And it is a number, so it might remain the same, it might increase, it might decrease. That's it. Anybody? What? You moved your lips, so. Increase, what do you say? Increase. Okay, so we have increase and decrease. Anybody for remain the same? We have everything. It's all about the way we wire them up. We have two options, in series or in parallel. If we're adding elements in series, it's like having one wire and then adding an extra after, so we're increasing the length. And when we're increasing the length, how does it affect the resistance? Increases, the resistance should go up. But if we have elements connected in parallel, we don't increase the length, we increase the area. So how does it affect the resistance? Decreases. The resistance should go down. By adding an extra element in parallel, we're decreasing the resistance. And when resistance decreases, but the voltage supplied is the same, how does it affect the current? I equals V over R. The denominator decreases. You see, it's too high. I have to switch the scale to this one. Because bulbs are identical, the total resistance of this circuit now is equal to a half of the resistance of a single bulb. So by adding an identical resistor in parallel, I cut resistance in half, which means I double electric current. Of course, what's going to happen if instead of adding this bulb in parallel, I will add it in series? Now I am doubling the total resistance. So my current now will be a half of the previous. This type of reasoning is very important. Okay, that's why we need to spend some time on it. So we have answered. Well, mathematically, we go from this to this. EMF R, EMF RR. But this is equivalent to same EMF, 1/2 of R. So I1, I2. And every time when we make a change, we have to draw a circuit for before change happened and after and look at actual values. So I1 will be equal to EMF over R, but I2 will be equal to the same EMF over R equivalent to I1. That's it, and that's not the question, but we saw this. We saw this. This is what is happening, and this electric current, I1 equals EMF over R. By adding an identical bulb in series, this electric current will be equal to the same EMF over R plus R. So now it equals to 1/2 of the initial. How do we know? We should see what kind of a connection is happening. You know. I just did it. All right. This will be my first slide tomorrow. You can start preparing. I will ask it for the web assign. Thank you. Yes.
I didn't understand the part where you did lots on the. I was going to be that you're going to connect them in parallel.